Math 2414, Other Convergence Test, Video 4, the comparison test. As its name implies, the comparison test allows us to determine if a series will converge or diverge by comparing it to another series that we already know converges or diverges. There does have to be a particular relationship between the two series, as you see illustrated here. We're going to call the series the sum of A's and the sum of B's, written right here. And the relationship between the two is that, well, first off, they both have to be greater than or equal to 0. So they both have to be positive terms, or rather eventually positive. So they can start out with a few negative terms. But we have to have this relationship between them where at some point one of them is always less than or equal to the other, eventually. Remember, eventually just means that that has to be true for all n greater than some other constant n. So there's a number on the number line, we call it capital N, so that when we go beyond that, this inequality holds. And it may hold for the entire, it may hold for all numbers, but eventually we have to have this dominant relationship where one of the terms is less than or equal to the other, but both of them are eventually positive. All right, so if we have that, there's one of two things that we can do. Number one, if the sum of the B's converges, then the sum of the A's converges. In other words, if the bigger sum, remember these are the individual terms, but if the bigger sum settles down and converges, then the smaller sum has to converge also. So think of it as if you have something larger than you that converges, then that forces you to converge as well since you're smaller, and vice versa. If the smaller sum diverges, then the larger sum diverges. In other words, if we add up a bunch of things and these things blow up, and the other sum adds larger things, then that sum has to blow up as well. It's almost like if you had, well, think about it this way. If we think about this as a floor, because it's lower than, and this one is a ceiling, then what these two theorems say is the following. If the ceiling converges, then the floor can't blow, then the floor has to converge as well. Meaning that if you have a ceiling that does not go to infinity and you are less than that ceiling, you can't go to infinity either, or vice versa. If you have a floor that is rising to infinity and there is a ceiling that is always above it, then guess where that ceiling has to go? It has to go to infinity as well. So if you think about it as a floor and a ceiling, the comparison test says two things. As long as everything's positive, eventually, as long as the floor is always above the ceiling, then if the floor converges to some number, then the ceiling has to converge as well. But if the ceiling diverges to infinity, then it forces the floor above it to blow up to infinity as well. Now, there are two things you cannot say. If the floor goes to infinity, you don't know what the ceiling does. Excuse me, I said that backwards. If the ceiling goes to infinity, you don't know if the floor goes to infinity also. The floor might converge to something, even though the ceiling goes to infinity. So what that would mean, and we're going to write this a little bit symbolically as a warning. Sum of the Bn diverges. In other words, if the ceiling goes up forever, does not imply that the floor also diverges. And similarly, if your floor raises but converges to a level, it doesn't mean that your ceiling does also. So if the sum of the floor converges, in other words, the smaller series converges, this does not imply that the larger sum, the ceiling, converges. So you have to be careful when you use the comparison test to make sure that you draw the correct conclusion. But if you think about it as a lower sum and an upper sum, the lower sum being the floor, the upper sum being the ceiling, and remember that if the ceiling doesn't go up to infinity, then neither can the floor. But if the floor goes to infinity, it pushes the ceiling to infinity. That's the two parts of the comparison test. But not the other way around. If the ceiling goes to infinity, you have no idea what the floor does. It may go to infinity, it may just go up a little bit. Or if the floor converges, then you don't know whether the ceiling converges also or if it keeps going up higher and higher. So to keep the floor ceiling analogy in mind, it's really easy to remember when you can and cannot use the comparison test. So let's take a look at an example. And in fact, the next two videos after this are examples of the comparison test as well. For this example, we're going to determine that the following series converges or diverges. Sum from n equals 1 to infinity of 1 over 2 to the nth power minus 1. Now, one trick for comparison is to ask yourself, how can I make this series easier by adding or removing a piece of it? In this particular case, if we remove the minus 1, in other words, if we compare it to this, yes, meaning versus, I know everything about that second series because that second series can be rewritten as the sum of 1/2 to the n power. That's a convergent geometric series. The ratio is 1/2. The absolute value of the ratio is less than 1, and therefore it converges. And we even know what it converges to, but that's not important. We just know that it converges. But before we say, well, this guy converges, therefore that guy converges, we have to establish the floor-ceiling relationship. We have to see which series terms dominates the other series terms. So we have to analyze the individual term versus the individual term to see which one is larger and which one is smaller. Now, some of these are pretty obvious. For example, on this one, it's almost transparent because in those two fractions, who has the larger denominator? The answer is the second fraction. Because the first fraction's denominator is just this guy minus 1. So we can instantly tell that the first fraction has a smaller denominator, and therefore it is the larger fraction. I don't think this is the problem I wanted. It wasn't, but I know which one I did want. I wanted a plus there. Because what we were accidentally about to do was the third example. Let me check my list real quick. Yes, I'm ahead of myself. So sorry for the sudden change in problem, but luckily we didn't have to change it that much. It was supposed to be a +1. So let me revamp the argument. I'm still comparing to this guy without the +1 because I know what this guy does. This guy, and we already said it, so we'll go ahead and write it. This is a convergent, I can spell, geometric series. Metric series, because our ratio is equal to 1/2, and more importantly, its absolute value is less than 1. So, but before we draw any conclusion about the original series, we have to establish the relationship about who's greater than whom. It is worth noting that both of these terms are always positive, so we don't have to worry about the greater than or equal to 0 part there. All right. But comparing these two, it should be pretty obvious that the first fraction's denominator is larger than the second one's, because the first denominator is 1 more than the second. And since the first fraction has a larger denominator, the fraction is smaller. But if you wanted a more convincing argument, you could start by saying that 2 to the n plus 1 is greater than 2 to the n. That should be pretty obvious. And when you reciprocate an inequality, you reverse the order. It's like saying if you cut a pizza into more slices, each slice is smaller. All right, so we do have this relationship, and as noted, everything is greater than or equal to 0. And by the way, it doesn't have to be greater than or equal to. It can be just strictly greater than. It wouldn't be wrong to change a greater than, or less than in this case, to less than or equal to, because it still allows it to be the correct order, less than. Okay, so we have two series. We have a green one in a green box and one in a pink box. And the one in the green box has the smaller terms. So here's what we know. if we were to write, and just for clarity, I'm going to write the sum of 2 to the n plus 1 is less than or equal to the sum of 1 over 2 to the n. And again, all of this is greater than or equal to 0. We're adding up a bunch of positive terms. So if we look at this, and we know that the one on the right converges, it was a convergent geometric series, then the ceiling of the one on the right doesn't go up to infinity. The floor is rising because we keep adding positive terms, but it can't get higher than the ceiling. And so by comparison, we know that the original series converges. It converges, well, regardless, it converges. So that's how the comparison, that's one way the comparison test can work. You compare one series to another, and you get the dominant larger series to converge. That means the smaller series must converge as well. In the next video, we'll take a look at another comparison test, and not to spoil the surprise, but this one we concluded therefore converges. Gee, I wonder how the next one's going.